Okay.
Hey, well, first of all, thank you very much for the invitation. It's a very good way to start my morning with the seminar talk. So today I want to explain this some work of me and my collaborators on the Fourier-Jacobi period, and in fact, I started to think about these problems or even this particular project since when I was in the graduate school. So Louis probably have heard of some part of this many years ago. So wait, is that better?
Yes, that's great. That's better.
Okay. So the main theorems that I'm gonna explain would be the joint work with Paul Boissou from Marseille and Louis Xiao from MIT. So they're both PhD students. Paul is a student of Raphael, and Louis Xiao is a student of Weijia. So I will essentially explain two things. So two subjects in the title. One is the Fourier-Jacobi period, and the other one is the relative choice formula. I will mainly focus on the choice formula on the unitary groups. At the end, I will say something about the case of linear groups. So first of all, what is this Fourier-Jacobi period? So the very classical example is also something that I really like, and it is the following. So we take two holomorphic modular forms, say f and g, and we take h. This is the half integral weight modular form corresponding to g by the Shimura correspondence. And we take a theta function, which is probably the most naive theta function that you would like to take. And then you consider this integral, which is the combination of the three. So you have f, which is a holomorphic modular form, and you have h, which is a half integral with the modular form, and you have theta, which is of a weight half. Then you multiply them together, and then you can integrate that on the fundamental domain, on a pseudo fundamental domain. And miraculously, this is related to an L function, which is of degree 6, and this L function is the symmetric square of f times g. This is quite a remarkable formula. I like it very much. So this is the so-called, or at least the left-hand side is the so-called the Fourier-Jacobi period, and in words, that's the trilinear form involving a theta function. So, well, now you see with we can write this thing in this period in a different form so that you probably can see the name Jacobi better. So this is the theory of Jacobi forms. So a Jacobi form is just a modular form in some sense on the upper half plane cross C. Now it has two variables. And now we have the Jacobi theta function, which is a two variable extension of the theta function that you had. Now here you see that if you let z to be 0, it has two variables, tau and z. Tau is on the upper half plane, and z is in z is in C. Now if you let z to be 0, then you get back to the theta function that you're familiar with. And the theory of Eichler and Zargia tells you that, well, we had h, which is half integral weight, and if we multiply that by the theta function that we had before, then this is in fact the restriction of a Jacobi form to the upper half plane. Now remember that Jacobi form has two variables. Now But if you let the second variable to be 0, then you get back to a modular form on the upper half plane. And Aker and Zargia tells you that the multiplication of h and theta is in fact the restriction of a Jacobi form, which I call capital F. Now, a different way to write the Fourier-Jacobi period is the following. That is, we restrict a Jacobi form to the upper half plane and integrate that against a modular form. In other words, we are looking at the period integrals of Jacobi forms, or in terms of the representation theoretic language, it's the restriction problems for Jacobi forms. So those are two ways of looking at the Fourier-Jacobi period. And hopefully this is going to provide us some insight later. So now let's get back to the general setup. So the goal of this whole lecture is going to be on the Fourier-Jacobi period on unitary groups. So we're going to introduce a bunch of objects. So we have the E over F, which is the quadratic extension of number fields. We have a bunch of characters. We need a non-trivial additive character. We have a quadratic character associated to this field extension. And we particularly have this mu, which is a character of the Hecker character of E, which is the extension, such that when we restrict this mu back to F, we end up with this quadratic character. So it's an extension of theta. And well, we want to speak of the unitary group, so we need an n-dimensional skew Hermitian space. And U of V, that's going to be the unitary group. You might be wondering why we need skew Hermitian spaces instead of Hermitian spaces. It's a bit more canonical using skew Hermitian spaces. Well, as before, we had F and G. Now we need two irreducible cuspid automorphic representations of U of V. We also want to speak of the theta function, so we need a Weil representation, and this Weil representation, which we call omega, this is the Weil representation of the unitary group, and this is realized on some Schwarz space. And you should note that this Weil representation depends on two characters. One is the additive character, as always, and for unitary groups, an extra character is needed, which is this character mu. So Fourier-Jacobi periods in one sentence, the one sentence description plays a role here. It's a trilinear form involving a theta function. So we take two automorphic forms, one from pi1, one from pi2, and the theta function. So the theta function is cooked up from some Schwarz space. So we take one Schwarz function here, and then we multiply 3 and then just integrate. That's the Fourier-Jacobi period. And the goal, as before, is to relate this period, the vanishing, non-vanishing, or exact value of this period, to the central value of tensor product L functions. And this is indeed one case of the famous Gangras-Prasad conjecture. This is the so-called the Fourier-Jacobi case. So this is the Fourier-Jacobi period, and this is what we want to do. So as always in this type of period integral considerations, before we can tackle any non-vanishing, global non-vanishing, or vanishing or exact value problem, there are always local considerations that needs to be taken care of before everything. So the consideration is that, well, if we consider this map, well, phi1, phi2, and well, sorry, they're both called phi. Curly phi, the curly phi1, curly phi2, and the Schwarz function phi. And this map to the Fourier-Jacobi period, if you consider this as a as a linear form, then it defines an invariant linear form, UV invariant linear form on pi1 tensor pi2 tensor the Weil representation. So it's in this home space, and well, if this home space vanishes, then there's no way that you can speak of any non-vanishing of the period because this home space simply vanishes. So a theorem of Sun Bingyong and Sun Bingyong and Zhu Chengbo tells you that, well, this home space, it's likely to vanish. The dimension is at most 1, so it's either 0 or 1. And the so-called the local Ganguras-Prasad conjecture actually gives a criterion when this space is of dimension 1 and when this space is of dimension 0. And that's the so-called local Ganguras-Prasad conjecture. And a few years ago, Gan and Ichino proved this in the PID case, and a little bit recently I did this for the Archimedean case. So this is not this is like the preliminary considerations before we can do any global work. So now I can introduce the L functions. So I want to explain the base change, or we're not trying to explain the base change, but get some assumptions on base change. So we had automorphic cuspidal automorphic representations pi1 and pi2 of the unitary group, and we can speak of their base change to GONE over the quadratic field. And we're going to make the assumption that this base change is an isobaric sum of these cuspidal representations of GON. So it's capital pi 1 isobaric sum, capital pi r, and so the assumption is that they are pairwise distinct, irreducible cuspidal automorphic representations. The important part is that they are distinct, and conjugate self-D, so that this thing itself is the so-called Hermitian other parameter. And this will ensure that we are essentially in the generic case. So everything I stated here is for pi 1, and we got similar assumptions for pi 2. So that's the base change, and the L function that we're going to be interested in would be the tensor product of the L function of the base change of pi 1 and pi 2. So here's the theorem. This is one of the main theorems that we have proved. So let the notation and assumptions be as above as before. So we're gonna assume that the home space is non-vanishing. Well, that's the preliminary consideration. So once we have that, then the following two are equivalent. First, the period is non-zero. Second, the tensor product L function is non-vanishing at the center of symmetry. Here half is the center of symmetry. So that's the theorem. You could also formulate this thing as the non-vanishing of the home space together with the non-vanishing of the L function is equivalent to the non-vanishing of the period. That's a different and equivalent way to formulate that, but I prefer this because this one seems shorter. So that's a main theorem, and this confirms the Ganguras-Prasad conjecture in this case. There's a more precise, refined form of the conjecture. For this one, we have to assume that this pi 1 and pi 2 are tempered. So in the tempered case, we can actually say much more because we can get the exact value of the period. Now, the statement is that the square of the period equals, here it's a product of a bunch of things. Here it's a power of 2, that's 1. And here it's a product of a billion L functions. This essentially comes from some volume terms. And it's so this is the main term. The next one is the main term, which is the central value of the tensor product L function over the joint L functions at 1. And finally, there's a product of local linear forms, and these are essentially the generators, locally defined generators in that home space. So we can get this exact form. But for this one, we need to assume that this pi1 and pi2 are both tempered. So the temperness is mainly used here in the local definition of these exact the explicit local linear forms, because we're integrating something, and that integral is only converging when this is tempered. We can slightly extend this, but not too much. So this is the second main theorem that we have proved. So so far I have been talking about the Fourier-Jacobi period for essentially for unitary groups like the UN and another one on so a cuspid automorphic representation on UN, and the another one also on UN. But there is a more general conjecture, which is also the part of the Gangler-Persad conjecture. It concerns the Fourier-Jacobi period, but you take one automorphic representation on a bigger UN, which is, let's say, UN plus 2R, and the other one is on UN. And you can also do a very similar construction. It's a trilinear form, but now this time you got to be more careful. You can't just multiply them and integrate, because you got two different groups. Now you need to take the Fourier coefficients on the bigger one and then restrict and do various stuff. So that one involves both the Fourier coefficient and something related to the Jacobi forms, or theta functions, and so hopefully this explains the name, the Fourier-Jacobi. We also proved the conjecture in that setup. It's the statement is more complicated, but we also proved that. So well, before we proceed, any questions regarding the theorems? Okay, let's just move on. So to better understand this Fourier-Jacobi period, probably it's a good idea to look back at what we know before. And indeed, there's in fact, I think, better known case of the period integrals, which is the so-called Bezout period. And this one is much easier to state. It does not involve any characters or no theta functions or whatsoever. So you take two Hermitian spaces, one of dimension n and one of dimension n plus 1, and you take two automorphic representations, one on one on UN and one on UN plus 1. And the Bezout period is kind of very easy. It's just you take one from one automorphic form on UN plus 1 and one on UN, and then you multiply them and integrate on the smaller group. So this is essentially, you are looking at the restriction problem of something from UN plus 1, and then you restrict that to UN. Okay, that's much easier. And in fact, there's a similar Gangour's-Prasad conjecture, which says that this period is also related to an L function, which is also this tensor product L function subject to the same conditions that we impose on the base change as before. And this one is known. It's so by now I think we can say, at least on the automorphic side, it's probably well known or completely understood. This is the work of many people, so I list many of them here. I had I'm not gonna repeat this long list of names, but it's in fact I think it's a major achievement of in the theory of period integrals or automorphic forms in general over probably the past 15 years. Jacquet and Rallis essentially initiated this trace formula project in 2008 or 2009 or something, and this was completed only recently, probably last year in 2023, and the progress here essentially covered my math career so far, and I'm happy enough to have witnessed essentially everything. So this is the Bessel period, and it's very easy to state. It's just the restriction problem. You get a bigger group and you restrict that to a smaller one. So now, if you recall from the very beginning that we have a different formulation of the Fourier-Jacobi period, something involving the Jacobi forms or the restriction problem for the Jacobi forms, and we can also do that here. So our goal is to write the Fourier-Jacobi form in the form of a restriction problem. So now we need to consider the so-called Jacobi groups in general. So first we have the Heisenberg group attached to V, which is just a V semi-direct product with F, and F here is the base field, and that plays a role of the center. So we should view this V as a symplectic space. It's the same space, but we have a symplectic form, which is the trace of that form, is a skew Hermitian form. And we have the Jacobi group, which is essentially the semi-direct product of the Heisenberg group with the unitary group itself. And the Jacobi form, it's an automorphic form on this Jacobi group. And the Weil representation, previously we said the Weil representation of the unitary group, but in fact the Weil representation is a representation of this bigger group, which is this Jacobi group. It's realized on some Schwarz space. So theta function, this is going to be the higher dimensional extension, higher dimensional analog of the Jacobi theta series. And here again, the same as before. Previously, we had the theory of Eichler and Zargia, and here it's the same thing, that this automorphic form phi2 times the theta function. This is the restriction of a cuspidal Jacobi form, which I call phi upper j, to the unitary group itself. So this is probably not something that everyone is familiar with. So let's take a more intuitive look what the Jacobi group looks like. So it looks like this. I like matrices, and if you write down everything in terms of a matrix, it's like this. So the Jacobi group sits in so we had the unitary group UV, and the Jacobi group sits in a bigger unitary group. So so previously we had UN, and now the Jacobi group is a subgroup of UN plus 2. And it looks like a parabolic subgroup of UN plus 2. Except that here we don't have those product of GOMs on the diagonals, but instead this is 1 at the two ends, And here in the middle, these stars will stand for the unitary group UN, which sits in the middle. And this unipotent part, which is these bullets, that's the entries of the Heisenberg group. So here, this upper right corner, that's the center, which is F. If you play with this, you're gonna see that this part is the center, and this row and column, and they determine each other, but you can use either one as your as that vector space V. So that's what a Jacobi group looks like. It looks like a parabolic subgroup. But because we get rid of those GLs, this thing is really unimodular, and miraculously it behaves in many ways like a reductive group, as we will see. So Jacobi forms would be automorphic forms on this thing. So once we have that, then the Fourier-Jacobi period, we can write that in terms of the Jacobi forms, and it's just like this. We take a Jacobi form, restrict that to UN, and then integrate that against a cusp form on UV. So in this way, the Fourier-Jacobi period takes exactly the same form as the Bessel period. And the only difference is that, well, for Bessel period, we're taking a UN plus 1 and restrict that to UN. But for Fourier-Jacobi forms, we're taking a Jacobi group and a Jacobi form, and then restrict that to UN. So they're essentially the same. Well, sorry, I'm not saying that they are the same. I'm just saying that they take the same form. So now I want to explain the proof or the general approach to this problem, and this was all initiated by Jacquet and Rallis, or if you go far back, these period problems. It's the so-called the relative choice formula of Jacquet. Jacquet invented this back in 1980s. So for Bessel period, there's a pretty well understood relative choice formula, and that's the choice formula of Jacquet and Rallis, and the progresses that I listed before are all about this choice formula. And now this one is essentially well understood. Most of the things that we want to know are known here. So inspired by this relative choice formula, my academic brother, also the academic brother of Louis, Liu Yifeng, he back in the graduate school, he was super strong at and he was inspired by this choice formula, and he proposed his own choice formula attacking the Fourier-Jacobi period. And this is the approach that we're gonna take. And this one's yet to be understood, and that's our main work. So at that time we were all in the graduate schools, like third year, fourth year, or something. And I was there looking for a problem to work on. I was very interested in this kind of automorphic form stuff, and I was looking for something, and I was talking with Liu Yifeng, and he suggested to me that at that time that well, he told me that Wei Zhang just worked out the transfer in the Jacquet-Rallis choice formula, so that was a major breakthrough at that time. And probably you can take that method and learn that method and see what you can say about this trace formula. And I was very happy to take this problem, and that was the starting point of everything here. So So the more you think about these things, the more similarities or analogies that you're gonna find. So a summary, a little bit oversimplified, the summary of the work. Well, if you look at our papers, it's the paper is about like it's pretty long. It's about 190 pages. You don't want to read that. But if you are seeking a one sentence summary of the work, is that, well, the former is well understood. Now you find the right formalism or right setup of the later so that the former techniques apply. And that's it. That's the, if you really want to bring something home from that paper, this is probably something that you would like to take. So for the rest of the talk, I will try to explain the analogy between the two cases and how we actually end up with some of our constructions based on the insight from the case of Jacobian lattice. So well, let's look at the Jacobian lattice case first. So we have the usual setup of the relative trace formula. We have the kernel function. So this is the kernel function on un cross un plus 1. We have the usual automorphic kernel function. And we consider at least formally this distribution, which is that we integrate this kernel function. This kernel function has two variables, x and y, and we integrate this kernel function on un for both variables. So because of some spectral decomposition that is well understood for this kernel function, so we should have, once we integrate this kernel function, we should get a spectral decomposition of this distribution, which is the sum of all the automorphic forms, and we take the Bessel period of both of them. So that's the spectral expansion of this distribution. So because we can vary this test function f, so our expectation is that if we could understand this distribution well enough, then we can extract the information from each individual terms. That's well, of course, this thing is not converging in most of the cases, then you need to be very careful here and there. There's a tremendous amount of work, but for heuristics argument, this is good. So that's the spectral expansion, and we would like to understand this distribution. So the way we understand this distribution is through the so-called the geometric expansion. Well, it's essentially an unfolding argument, because what you can do here is that you have this kernel function, which is the sum, and you are integrating something. You're integrating the sum, and then you can unfold the sum. Now, the unfolding miraculously will give you something called orbital integrals, and these orbitals. So this distribution unfolds to a sum of orbital integrals. Again, this is not converging at all. It's very far away from being converging, but it doesn't matter. Let's look at this only heuristically. And the orbits are here are like double cosets. And we have we have this un cross un plus 1, and we have two uns. One act from the left diagonally, and the other one act from the right diagonally. That's the action. And well, this action is hard to understand directly, but we can somehow look at this at least at the so-called infinitesimal version, which is the action on the tangent space at the origin. And that's somehow you should think of this as some sort of local information at that place. And this one is much easier to understand if you simplify this action a little bit, and then you're going to see that the so-called infinitesimal version is in fact much easier to understand. It's the unitary group. It's the un acting it's the conjugating action of un on the Lie algebra of un plus 1. And if this action further simplifies to the unitary the UN acting on conjugating action on the Lie algebra of itself cross the Hermitian space. So this, well, it's just the conjugation action and the normal multiplication of the unitary group on a vector space. So this one seems much easier to understand. And in fact, all the study of orbital integrals, essentially everything should go through this infinitesimal version first, and then go back. So this is the case of Jacquet and Rallis. Now let's look at the case of Liu Yifeng. Again, we have the distribution. As before, we have the kernel function. And we have this distribution. Now, this kernel function is on UN cross UN, and we have the kernel function. And now the distribution needs a bit care because we want to get the Fourier-Jacobi periods out. So we need to multiply the theta functions and then integrate. So the spectral expansion, well, as before, we should get the sum of automorphic forms. But now here it's the sum of the Fourier-Jacobi period because of this particular kernel function that we take and the particular shape of the distribution that we take. We have the theta functions here. So we have this spectral expansion or expected spectral expansion. So now here it's got to be the one thing to note is that, so in the definition of the Schwarz functions, there's a, in the definition of theta functions, there's a Schwarz function. And this Schwarz function needs to be considered as a test function together with this f. So we now have three test functions. We have this test function on the group, and we also have two Schwarz functions as test functions. And we can vary. So this is the geometric side. Now, this is the spectral side. Now, the geometric side is something that you need to be a little bit smarter in order to do it. There's a pretty tricky Fourier transform. Because you see that if you directly unfold this, then you suddenly get stuck because you have these theta functions here, and it's hard to unfold these theta functions. But the argument here is that we can make a Fourier transform so that we in fact essentially get rid of those theta functions, or at least get rid of one of those theta functions, so that the action is easier. So we have this Fourier transform, and we define some integral transform of the test functions f and phi1 and phi2, and we now get some new test function, which is like simplified test function. But the upshot is that we have an action of uv on uv cross v. The first component, the conjugate action, and the second one is the usual multiplication. This is the first we get this action. Second, we get a geometric expansion, which is in terms of the orbital integrals of this action. So this is the work of essentially the work of Liu Yifeng. So the analogy here is that this is very similar to the geometric side of Jacquet and Rallis. And in fact, if you look closer at this, they have the same infinitesimal variant. So I'm not writing the infinitesimal variant down here, but the infinitesimal variant of this is again the unitary group conjugate a joint action on the Lie algebra of itself, and this is the second one is the multiplication. If you look at this, the action is exactly the same. So even with this very simple observation on the geometric side that they have the same infinitesimal invariant, we can already say something non-trivial towards the Ganguers-Prasad conjecture, and this is indeed what I have done in the graduate school. I wrote some papers proved some cases of the Gross-Prasad conjecture, and probably I also gave talks there, so Luis probably have heard of these things up to this point. But well, those papers are not great. Looking back, they're not even well written. And we want to achieve better results. We want to achieve complete results. Well, in order to do that, then we need to do more work, especially on the geometric side, and we also need to truncate the trace formula properly and work out everything. And that's the main work of the manuscript of the recent manuscript that we released. So because we want to achieve the analogy, we want to write the trace formula of Liu Yifeng in the same form of the Jacquet and Rallis in order to achieve better analogy. And in this way, we need we're going to jump back to the Jacobi groups. So we had the Jacobi groups and we have a bunch of test functions. So now we just do some integral transforms, just some sort of Fourier some kind of Fourier transform and so on. So from it's a bit complicated if I write down here, but what I'm doing is that we have a test function on the unitary group. We have two test functions, phi1 and phi2 on their Schwarz functions, and we do some integral transform so that eventually we end up with a test function which I call f tilde on the unitary group cross the Jacobi group. So this is something that you should take on this page. You don't need to worry about how I actually do it. We can do it. Well, now we have this test function f tilde, and if we just naively mimic the automorphic kernel construction, then we can form the automorphic kernel on the Jacobi group. But suddenly, if you see that if we restrict that automorphic kernel back to the unitary groups, then we end up with a very familiar expression as before. It's the kernel function on the unitary group times two theta functions. So the upshot is that the kernel function, the kernel function in Liu Yifeng's relative trace formula is essentially a kernel function on the Jacobi. So the Fourier transform, the complicated Fourier transform that we had before it's nothing but just an integral transform that takes the test function to a test function on the Jacobi group. So now we can consider this distribution, which takes exactly the same form as the case of Jacquet and Rallis, which is we take a test function on the Jacobi group, and we form a kernel function on the Jacobi group, and then we integrate over the smaller unity group. So that's the distribution, and this is a more compact form of that distribution. So this looks very much the same as the case of Jacquet-Rallis, and well, for the pure beauty of this, I like it. But more importantly, this suggests a right way to truncate the relative trace form, and that's the important part. Well, I'm happy. Well, that's not important. It's whether we can do this or not. That's more important. If I'm happy, but I still can't do it, then that's nothing. So for the comparison, you see that previously we have this complicated kernel function, which is the kernel function times theta functions, and that's very hard to truncate because of the theta functions. But now if we write this in a more compact form, then we can it's a pretty straightforward thing. Okay, so now the modified kernels. We have so again, let's look at the case of Jacquet and Radis first. So what does a modified kernel look like? A modified kernel is alternating sum of the constant terms, essentially. You need to put in some characteristic functions here and there, but it's essentially essentially just the alternating sum of constant terms. So here there are two things that are important. So what are those constant terms that you are using, or more precisely, what are the parabolic subgroups that you are using? That's one. And second, the constant terms are not automorphic, but you need to make them automorphic. So on what group that you're summing over, those are the two important things in the modified kernel. Here I will emphasize here I will emphasize the use of the parabolic subgroups. So the parabolic subgroups that we're using, so because we're considering the kernels on the product of two groups. So the parabolic subgroups that we're using is a parabolic subgroup of it's a product of parabolic subgroups Pn and Pn plus 1. They range over all standard parabolic subgroups. You fix the notion of a standard some way, such that the intersection of the bigger one with the small group is the smaller parabolic subgroup. This is the parabolic subgroup that we're using. So the summation is over the smaller group. That's well understood. So this is the modified kernel of Jacquet and Radis. Okay, now we make some slight modifications. So we end up with our modified kernel. Now we have the modified kernel on the unitary group and the Jacobi group. It's a test function there. So we again do some modified kernel. It's again the alternating sum of some constant terms. And here we need to pick carefully the parabolic subgroups. So as before, just mimicking what Jacquet and Radis have done, well, we have this parabolic subgroup is just a parabolic subgroup on the unitary group and the parabolic subgroup of the Jacobi group, such that the intersection with the unitary group is the smaller parabolic subgroup. So everything stays the same, except one thing, that is the Jacobi groups are not reductive groups. And well, even though there is a well-defined notion of the parabolic subgroup of algebraic groups in general, those are not the parabolic subgroups that we actually want. So so the next slide will explain what these parabolic subgroups are. So we are looking at a parabolic subgroup of a Jacobi group, but let's first look at the parabolic subgroup of a unitary group. So a parabolic subgroup of a unitary group is just a stabilizing isotropic flag in V. Now we just define the parabolic subgroup, the parabolic subgroup. It's not the actual parabolic subgroup. The parabolic subgroup of the Jacobi group to be a semi-direct product like this. Well, it's a bit abstract if I write it like this. On the next slide, I will show you pictures. But the Levy part is just the product of GLs and the smaller Jacobi group. Sorry, not the next one, but this. So this is what a parabolic subgroup of a Jacobi group look like. So it's a parabolic, so inside here, inside this UV part, it's a parabolic subgroup. And inside this Heisenberg group part, you take some part of the Heisenberg, essentially. And the Levy is so this is the Levy, and it's a product of GLs and the GLs and a smaller Jacobi group. So this is a, so if you look at the diagonals, the first and the last component is the product of the GLs, and the rest, this star and the combinations of these bullets will give you a smaller Jacobi group. So that's the parabolic subgroup of the Jacobi group, and it turns out that this is the one that works. And because of this particular construction, parabolic subgroups of the UV and the Jacobi group are in one-to-one correspondence. So this was our very initial attempt, and this is correct. Of course, it's correct. It has to be correct. But it's not that convenient at various places. For example, you need to redevelop the automorphic form theory for the Jacobi group. For the Jacobi groups, it's doable, but it's going to be a long argument. For example, you do want to get the long length decomposition for the Jacobi groups. That's something that I don't want. So we discovered later that these constant terms in terms of these Jacobi groups of the so they can be reformulated a little bit in terms of the partial theta functions. So basically, for the theta functions, you take the summation of the Schwarz functions. But partial theta functions, that you take the summation of some part and you integrate some part and you evaluate that at zero for some other part. It's like a mix of various evaluations. That's the so-called the partial theta functions. And we can reformulate everything in terms of the partial theta functions. So the Jacobi groups, even though it plays a major role in the way of thinking, finally it does not it does not appear in the formulation, but only in the proof. So that's the unitary group side, the relative choice formula on the unitary group. Essentially, we reformulate everything in terms of the Jacobi groups and mimic what Jacquet and Radis did, or what has been done for Jacquet and Radis. That's the unitary group situation. Now I have 5 minutes, which is perfect. I'll explain the last part, which is the case of GLN. It's essentially the same, except that the Jacobi groups here would and the parabolic subgroups here look a bit different. So I'll be a little quick. So we need to compare the Fourier-Jacobi period with this tensor product L function, and the tensor product L function comes from the Rankin-Selberg convolutions. And the Rankin-Selberg convolution, it's GLN cross GLN, so the Rankin-Selberg convolution will involve a merabolic Eisenstein series, and the merabolic Eisenstein series is essentially a theta function. It differs from a theta function by integration on the center, but here I directly take this theta function. So we have this theta function, we have the test function on GLN cross GLN, and again we have this distribution. So this distribution is the kernel function on GLN cross GLN. Now on the first variable, we multiply it by the theta function and then integrate on GLN. So this one will give you so the first integral over H will give you the Rankin-Selberg convolution, and you will see the L functions from the first integral. Now the second integral is on the second integral on the other variable, this G prime. I integrate this G prime on GLN F cross GLN F, and that detects functoriality. Basically, we only want the base change L functions. So the second variable here, the integration of the second variable here will isolate those base change automorphic representation. So that's the distribution, and here again we need to take the consideration of the Jacobi groups, and now here the Jacobi groups looks like this. It's essentially the same as before, but we have more inputs. We have GLN in the middle, and we have a row of a row vector here which are these bullets, and the column vector here, this is these circles, and we have the star, which is the upper right corner, which is the center. So here the difference is that the row and column, they're independent, they won't determine each other, not like the case of unitary groups. So this is the Jacobi group, and again, to obtain the correct truncation, we need to understand the parabolic subgroups of this. So the parabolic subgroups of this looks a bit more complicated. It's more complicated than the unitary group situation. There are two types of parabolic subgroups. First, it looks like this. You don't have to know what they are, but the feature is that the levy is a product of GLs. And there's another type such that the product, the levy is a product of the GLs and a smaller Jacobi. So they are pictorially, they're like this. And again, as before, we would for the truncation, we need to consider the standard parabolic subgroups of the Jacobi group, such that its intersection is the intersection with the smaller group is the smaller parabolic subgroup, and to each parabolic parabolic subgroup of the Jacobi group, we can define the partial theta function, and then we form the modified kernel, just as before. Now, if we get back and make a comparison to the work of Zito on the formulation of the modified kernel, his modified kernel is again as before, just like this. You have something on GON cross GON plus 1, and it's an alternating sum, and he's using the so-called the Rankin-Selberg parabolics. And what are they? So his parabolics are Qn cross Qn plus 1, which is a parabolic subgroup on GON, and another parabolic subgroup on GON plus 1. With the condition that the intersection of the bigger parabolic subgroup with the smaller group is the smaller parabolic subgroup. Qn plus 1 intersect GON is Qn. But with one thing to note, that is Qn has to be standard. Qn has to be standard. That is, the smaller parabolic subgroup needs to be standard, but the bigger one does not. The bigger one might or might not be standard. It's a semi-standard parabolic subgroup such that the intersection with the smaller one is standard. So we're making use of not just the standard parabolic subgroup, but some non-standard ones. So miraculously, it turns out that there's a canonical one-to-one bijection. This is not that obvious, but you can write this thing, really write this thing down explicitly. There's a canonical one-to-one correspondence between the parabolic subgroups used in our modified kernel, that is the parabolic subgroup of the Jacobi groups, with these so-called Rankin-Selberg parabolic subgroups that Zito used. So it's really a perfect match. So this enables us to study our modified kernel using the method of descent. So we can essentially descend everything to the infinitesimal level and invoke some theorems of Zito and Shaldwell. And that's how we study our modified kernel. So to summarize, first, our truncation method using parabolic subgroups of these Jacobi groups suggests a way to truncate the period integrals involving theta functions. For example, we can truncate the Rankin-Selberg convolution. We can truncate that. So we can do the Rankin-Selberg convolution, say, for Eisenstein series. Second, this is something that I don't quite understand that. So we got two very different relative trace formula, and by descent, they are led to the same infinitesimal variant. I don't know why. I don't know if that's just a coincidence or it's something deeper. And I don't know how to make better use of it, and I'm not happy with it. So that's it. Thank you.
Thank you very much. Let me stop the recording. I think maybe, Ricardo, I think I'm not able to stop it.